You know what's mind-blowing, ninjas? Most people think these two expressions are equal, and are they correct? Well, you're gonna have to stick around because the answer to this one is not what you think, because you might be making this mistake too. I'm gonna start with the left-hand side to see if I can make it equal to right. So for sine of x over tangent of x, I can break this fraction up as a product of two terms, which helps me visually to understand this. So sine of x times 1 over tangent of x, remember that because tangent of x is the same as sine of x over cosine of x, we have a -1 power here because we were working with 1 over tangent of x. So essentially, the sine and cosine terms for the fraction are going to get inverted, bringing the sine of x to the bottom for the denominator. And check this out. We can cancel sine of x terms, giving us a final expression of cosine of x. And we're done, right? Well, not so fast, because a problem here is we have now changed the domain of the original problem I gave you. I want you to try something. Graph the original problem I gave you and see if there are any values of x where that function isn't defined. You're going to notice that, in fact, there is a problem here because cosine of x has no domain restriction. Remember, domain of sine of x is all real numbers x, and that's the same for cosine of x. So it can't be the case that sine of x over tangent of x equals cosine of x everywhere. So what I want to do in this video now is I want us to define what the domain restriction is for sine of x over tangent of x, and stick around because at the very end of the video, we'll conclude whether or not the two functions truly equal each other. So for sine of x and cosine of x, remember that they're defined everywhere, but for tangent of x, we want to figure out if it's not defined for any value of x. Well, because tangent of x is the same as sine of x divided by cosine of x, you know you can't have a denominator of 0 because dividing by 0 is not allowed. So we can write the domain as the set of all real values x, where cosine of x is not 0, for this expression sine of x over cosine of x. Now, we need to be a little bit more formal here and really define what specific values make cosine of x 0. So for this case, what I want to do is go back to the unit circle and graph it, because visually it helps to see what the answer is. For the unit circle, if you remember, you have a radius of 1. I'm drawing an angle here, theta, and for any point on the circle, normally your x component would be r cosine of theta, where r is the radius, and your y component would be r sine of theta. But for the unit circle, r is 1, right? So it's just at a coordinate point of cosine of theta and sine of theta. And we want to figure out, okay, your x component, this cosine of theta, where is it going to be 0? Well, I marked the two spots on the y-axis. It's going to be 0 at the possible values of x is 90 degrees or 270. And I'm also going to be working with radians primarily when defining the domain here. So if you remember, 90 degrees is the same as pi over 2 radians. Think of pi as 180 degrees. And 270 degrees is the same as 3 pi over 2. But we can't stop there, right? Because going back to this circle, there are actually infinitely many angles. Think about going around and around and around so many times, right? You could have angles like 90 plus another 360 degrees. You can go in the reverse direction. So here are some sample values that make it 0. And this always helps to write out several values, right? Because then that's going to help us formulate the final domain expression where cosine of x cannot be 0. So I want you to think about it. Leave it in the chat below if you see how to write that expression. If you don't see it, that's okay. What we're going to say now is, okay, for cosine of x, it's going to be 0 for any of these angles where we see something in common, right? In all of these cases, we have some sort of a fraction where you've got an odd number times pi, all divided by 2. So negative pi over 2 is the same as a -1 times pi over 2. We've got 5 pi over 2, etc. So this helps us to write out when the angle is going to make cosine of x 0, right? Essentially, it's any odd multiple divided by 2, all times pi radians. So in other words, x is going to be this expression. Any angle that's 2k plus 1 all over 2 times pi radians. Because 2k plus 1, where k is any integer, guarantees that the numerator is going to be an odd number. Try it for yourself. Okay, so that's the case of cosine of x. Now we're done, right? Well, again, not so fast. You got to be really careful here. Remember that for sine of x over tangent of x, we just defined the cases where tangent of x is not defined, but we're actually not done. There's still another big trap here. I'm going to rewrite the original problem again to help you out here, because sine of x over tangent of x, if you remember, can be rewritten as sine of x times cosine of x over sine of x, where here above we canceled out the sine of x terms. But I'm going to leave them here as is because I want you to notice something here. We found out the cases of tangent of x not being defined when cosine of x is 0, but here we're also noticing that sine of x is appearing on a denominator. So we have a second restriction, believe it or not. Sine of x cannot be 0 here because we'd be dividing by 0. And so once again, we go back to the unit circle, and now it's these 2 points. So in other words, whenever now you're on the x-axis instead of the y-axis, you're going to find out that sine of x is in fact 0. And this one's an easier expression to write. I'll just skip ahead a bit, but ultimately you'll notice that it's going to happen at 0 degrees, 360, 720, going in the reverse direction, negative 360 degrees. So in other words, any integer times 2 pi radians. Okay, so now what I want to do is I want to find the final domain for the original problem I gave you, sine of x over tangent of x. And the way I'm going to do it is I want to bring in now this restriction we just came up with here for sine of x, along with the restriction we found earlier for cosine of x. So we have these 2 cases now, right? For sine of x, we only have 2 pi k radians for the values of x that are allowed. And then for cosine of x, it's a little different. We have increments of halves. So think about how you would combine these two and let me know if you see it. Okay, a way to visualize this, right, is 2 pi is the same as 4 pi over 2, right? So we could rewrite the sine of x case to be in terms of halves, just like cosine of x. And the way you're going to bring these together is the domain of sine of x divided by tangent of x will be all real values x, where x is not an angle, that is k pi over 2, where k is any integer. And try some sample values, right? If k is 0, you end up on the x-axis, which is not allowed. If k is 1, you end up on the y-axis, which is not allowed. Try negative values and see for yourself. And this brings us to the final question and the answer for this video of whether or not sine of x over tangent of x equals cosine of x. And the answer is